Welcome, my friends. My name is Esteban Solari. I'm working in clinical research at the University of Munich, and I'm presenting this hands-on tutorial on segmentation using the UNet for medical imaging. Course is sponsored by Hybrid and the European Union. This Hybrid is a big network of collaboration between companies and universities in the entire Europe that basically are trying to develop new technology for hybrid medical imaging. This is a basic example, but it's a really powerful one. The UNet is one of the most powerful segmentation deep learning networks that we know. And I will show you how to program it from scratch. But first, we need some introduction. What you need in advance is a basic knowledge of Python, of course, then some knowledge of artificial intelligence, machine learning, deep learning in general, nothing too specific, but you do need to have done the previous steps in the hybrid online tutorials that we are doing. So you need to know a little bit about how does a deep neural network works. You need to know a little bit about what segmentation is, some examples in the medical imaging community, for instance, and you will need to know a little bit of math, particularly university math, but not really. We are not going to go really technical in this sense, only to understand the functions that we are using. So what you will learn, first, the difference between a neural network and a convolutional neural network. The convolutional neural networks are at the core of the UNets that we are going to use, so you need to understand how a convolutional neural network is different from a neural network in general. And then also the power of the fully convolutional neural network. So the basics. First on math, a convolution, as you can see here in the animation, is basically a matrix product between a matrix or an image and a kernel. You see that we already have the numbers of the kernel, so this is a fixed kernel, and this is basically detecting some borders in this image or matrix. You can see how it works. You start first with the first 9 elements here, and you multiply these numbers with these numbers, and you have the result in the first pixel in the result matrix. And then you move a little bit and do the same thing with the next, and then the next, and then the next, and then the next, and then you complete the entire result matrix. Pooling is another interesting operation, and it's basically to downsample an image. For instance, in this case, we are doing max pooling. That means that we are taking, for instance, dividing these images in 4 and taking only the max value of these 4 regions. So the max value of here is 20, so you put it here. The max value of here is 30, so you put it here. And this is pooling. It is a technique to downsample, so to make images smaller, basically. Then the deconvolution or upsampling is basically a process where you do exactly the same as in the convolution, but backwards. So you try to recover the image from a previous convoluted result. This process is also a process of upsampling. So in some sense, we could say that is the opposite of pooling in this context. Finally, activation functions. You will use activation functions at the end or at the beginning of a layer in a deep neural network. They are really basic functions. We are only going to use 2 of these. The ReLU is a really popular one, and it's basically keeping all the values above 0, but making all the values that are negative 0. This is a strongly nonlinear function, so it will introduce some nonlinearity, so you get predictions that are more complex. Finally, the sigmoid function. Normally you will use this when at the end of the deep neural network, when you, instead of wanting a result that is between any numbers, you want a result that is basically between 0 and 1, for instance. So basically you will just multiply all your values into this sigmoid shape, and then you will only keep values between a minimum and a maximum that you set. So convolutional neural networks. This is a convolution, as we already said. It's basically a matrix multiplication between a matrix and a kernel. This is a neural network. So you start, for instance, with an image. You flatten the image. You make it like a vector. And then you try to build a lot of connections between this input layer, that is a vector, and the next layer. And the deeper you go, the stronger will be the interpretations, but also more image you need to train it. So in this case, you will first train this network, and to do that, you will use an image that you know is a dog. You will put it here as a vector, and you will ask the network, is it a dog or a cat? And 50-50 it will say it's a dog or a cat because it doesn't have any training. If it answers correctly, then you will give him a positive feedback, and if it answers incorrectly, then you will give a negative feedback. And the network will change its weights inside the deep layers to try to predict correctly the next time that this is a dog. And when it's already trained, then you will just feed this first input layer a picture, and it will tell you with much certainty if it's a dog or a cat. In this case, 95% a dog, 5% a cat, so you will assume that this is a dog, and correctly so. Finally, the convolutional neural network. This is the right or the better way to do neural networks with images. Because in the first case, you have to flatten the image into a vector, and you lose all the spatial connections between two voxels. But here, you keep the spatial connections by doing basically, instead of using these simple connections, these simple node connections, you start using convolutions. And you will perform a convolution with some kernels inside here. But those kernels are not going to be fixed like here. These kernels are going to be trained. So you will give this convolutional neural network a number, and you will train it to always say that this is a 2. And these kernels are going to change until the majority of the numbers that you feed this network will be correctly interpreted in the output. So that's a convolutional neural network. It's a neural network, but it uses convolutions between layers. So a particular convolutional neural network is called fully convolutional network. It was developed in 2014, and it revolutionized the way we do segmentation with neural networks. You can see here that you start with an image, and then you apply a convolution, and then apply more convolutions, and these are going to be downsampling the images. So in these first layers, you will have a lot of spatial information, but then as the convolutions go, then you will lose a little bit of the spatial information, but not all of it. And you will get to these semantic layers. These semantic layers are basically layers where you have some spatial information because you didn't lose all the dimensions, but you have mostly information about the meaning of these things. So if there are two objects or one, if it understands that these are different objects or the same, etc. And instead of just saying this is a dog or a cat, you will try to upsample again, and your result will not be a yes or no or a semantic result. It will be an image. And this image, if you train it with, for instance, segmentation mask, if you train it with the shapes of the dog and the cat, it will learn to segment or whatever object you train it to learn. So in this case, it's a really powerful tool. But there's in 2015, 1 year later, there was another paper that used this fully convolutional network idea, but got it better, at least for biomedical image segmentation in this case. You can see here that these are of all convolutional neural networks, but it has a particularity. It has a downsampling period and it has an upsampling period. This has a U shape, and that's why it's called UNet. It's also symmetrical. This is also another particularity. And you can see that when you start the network with this input, it will go through some convolutions, but then you will get some downsampling. So in these first convolutions, you basically are learning the spatial relationship between different pixels here. So you will have a lot of spatial information. But if you go down here, downsample with our max pooling, you will start losing some of the spatial information, but you will gain like more general spatial information. For instance, if you here know the relationship between two really close pixels, here you will know the relation between, for instance, two bubbles. And here in the smaller layer, you will know the spatial connection between farther away bubbles, for instance. In this last layer, this is called a semantic layer. Uh, this already doesn't have much information about the spatial characteristics of the image, but it will have mostly information about the semantic characteristics of the image. So it will have more general characteristics of the image. So if we go all the way down here, you lost most of the spatial information. But since you want to segment an image, then you will need to recover that information. So you will first try to do that, but upsampling. Upsampling convolutions will give you bigger and bigger images until you get like an image with the size that you want, the exact same size as you started. But you're going to add something that is really important in this unit. That is the concept of skip connection. Skip connection is basically copying the results of this first spatial convolutional layer. You copy it to the input of this spatial convolutional layer that is in the output. And then you do the same with all layers. So in this layer, you perform some convolutions, and at the end, you copy this result here all the way here before doing the downsampling. So when you upsample, then you will train your new layers with the information of the upsampling, so the semantic information that is being upsampled, but also with the spatial information that you didn't lose between here and here, just because you are copying it and then training a layer again. So in every layer, you are going to train with semantic information, but also with spatial information. General spatial information and more close by spatial information. So you will have different layers of spatial information and also different layers of semantic information. And all of those are going to be trying to train how to segment this image. In this case, how to draw the bubbles around here. So we're going to try to program this small UNet network. Just some concepts. As I told you, this is the input and output. You have a downsampling step and an upsampling step. You have a semantic layer, and you have skip connections. We explained all of those already, so we are ready to go and start our programming. So see you in a second, and get ready your Python skills because you're going to need them. So now we are in our Python environment. In this case, we're going to use PyCharm. We are going to use pre-written codes because otherwise it's going to be impossible. It's really long, but you will get the idea and you will be able to copy whatever you want from these codes. It's not a problem. We are going first starting to do the general model. So basically we are going to import some functions from Keras. We are going to use Keras for the backend of this deep learning model. We are going to import models, optimizers, because we need some optimization functions for the training. Then we're going to add some checkpoints, and the backend will be Keras. This is going to be simple. This first step we simply set in the model. So we are going to define a unit. This is just a function, and this unit will have pre-trained weights if we want, and an input size as a parameter that we also need. It can be an image, or it can be a colored image, for instance, if we have more of these values here. So the model we will define as the function model from Keras, and we will have an input and an output. This input, we still didn't define it, but it will be what we call an input tensor. So it will basically be an image, and then we will have an output that is, it will be called last layer. And with this model, what we want to do, we want to compile it. That just means that you build it. So after we finish doing the entire model, we are going to build it in the memory. And it will work with another optimizer in this case. Just this you can learn later what this means. There are many optimizers that you can use. And the loss function will be a binary cross entropy function, and we are going to measure the accuracy as our parameter to know if the network is getting better or worse. And finally, if there are pre-trained weights, we are going to load them. So what are the weights? Of course, the weights are the things that the network is learning and that then is using to solve some problems, for instance, to segment or to say if this is a dog or a cat. So all these learned weights, we can load pre-trained weights. So if we want, for instance, to retrain a network with extra information, we just load the previous weights and then we retrain it. Well, this is the basics of the model building. Now we're going to add some extra information that's going to be about the input and the output. So for the input and the output, we're going to need some extra imports that we're going to copy from here. This, and then we're also going to need an input and an output. So basically, as I told you, the input and output are really easy to define here. The input is just an input tensor. In Keras, you will call it as input, and it will have the shape of the input image that we define that is going to be the size of the input in the unit. And finally, the last layer, our output, will be basically two-dimensional 1x1 convolution. This is because, as we saw, the last layer of our network will be basically just a sigmoid activation layer. So this is basically doing the job of the sigmoid. And here in between, we're going to have to put all the layers of the unit. So now we only have like the input and the output. And once we have the input and the output, we build the model. But now we need to do all the layers. They're going to be, of course, in between the input and the output. And we are going to take them from here. So these are some functions from the Keras layer module. Convolution 2D, we are going to use this to do convolutions. Max pooling 2D for the downsampling step, and dropouts. It basically helps to reduce the overfitting of a model, and it works by randomly dropping some weights in the kernels, and in that way it will stop the network to overtraining to know only how to classify the images that we feed them during the training, and will be better to predict images that are not in the training set, so not normal images, other images. So we're going to copy all these layers, and we are going to go through them really fast because there are too many, but you will get the idea of how they work, so you can also implement them yourself. They are going to be, of course, in between the input and the output, and you can see that these are a lot of layers, but these are exactly the layers that the graphic of the unit has. So this is annoying, but we'll have to do this because we want this to compile correctly. We can see here that we have an input layer, and the input layer includes two convolutions with an activation function of a ReLU. Basically, padding same, this thing here means that we don't want, in every convolution you always lose information in the borders, as we saw before, and that's why it's normally like a downsampling step. But with this padding same, we're basically telling the machine we don't want to lose the borders, so at least if we lose the borders, then complete them. And the kernel initializer is basically in the first run of this network, what is going to be in the kernel? Are going to be only zeros, or are going to be random information? And we, in this case, we selected one kind of normal distribution that we like. And at the end of the layer, we're going to do two things. Here first, we're going to do this max pool. So basically, this is going to be the downsampling step for the next layer. That is this first downsample layer. And you can see that this input max pool is going to be used as the input for the first layer in the first downsampling layer. Okay, the first downsample layer, we also have two convolutions and then a max pool. And we can see that all of the layers are going to be exactly the same. So you see that this is not really difficult to do once you understand how to do it. Like we did the first step, and now we can do all the steps exactly the same. So we do the first max pool, and then we feed it as an input of the second layer, downsample layer. And this second downsample layer, after the convolution, you feed it again to the second convolution, and this we feed it again to the max pool. And this max pool, so that's downsampling, you will feed to the third downsample layer that we have here. And the third downsampling layer is exactly the same as the previous ones. But you can see here that we already have something different. And it's this dropout step that we are adding because we want to make it before the semantic layer. We want to make this more robust, less prone to overfitting. After the third max pool, we are going to the semantic layer directly. This semantic layer will also have two convolutions and a dropout. But no max pooling now, because what we don't want to do now is upsampling. Max pooling is for downsampling, so we're going to do upsampling. And to do the upsampling, we are basically just implementing a convolution. And within this convolution, we can say we don't want to convolute only the semantic dropout layer here, but we want to do that with this upsampling to this step. So it's the same semantic dropout layer, but it's upsampled to twice of its size, basically. So now the same thing as we did in the downsampling steps, we basically go all the way up, but instead of using the max pooling, we're going to use all the time this strategy of upsampling the first layer. You see that we here also upsample the first layer, and then we are going to add some extra information here in the upsample layers, and it's what we were talking about. To keep the spatial information in the last layers, we're going to add these skip connections. So in this first upsampling, we add a first skip connection, and in skip connection is basically we'll use the function concatenate, and concatenate basically just puts together two matrices that have the same sizes. So in this case, we are going to put together the third dropout and the first upsample. So this first layer of the upsampling and this last layer before the max pooling of the last downsample, as we see in the image now. So now we're going to go up all the way, and we are basically doing exactly the same all the time. We don't change anything. It's exactly the same, just more convolutions and more skip connections. And more upsamplings, of course. And that's it. Basically, we got to our output layer, And in our output layer, we will have all the convolutions, also the skip connection, but we will join the results of this last layer, this output layer. We'll join that now with our last layer that we already programmed before. That is basically a convolution 2D, and now with an activation function of a sigmoid. And it's a one-to-one convolution, so we don't lose information or size. So basically, the last layer is basically connecting this output layer with the last layer. And now that we have an input layer and an output layer, we can create our model and then compile it. That's it. That's all it takes to create a model in Python for deep learning purposes. And this is basically our UNet model. Now we are going to see how to use it, but it will compile as soon as we call this function and get to this point here. And then we can use this model to get some really cool results that we are going to see. We finally finished to code from scratch our UNet model, so now we have to try it. First of all, I want to show you what is it, our model basically. Our model is this, our UNet now that I just defined, and we're going to see a summary of what we just programmed. You can see here in this summary that there are all the layers that we programmed, layer by layer, with the poolings and the convolutions. But in the end, this is what is really interesting. There are 31 million different parameters that we are going to have to tweak. So that's why the training takes so long, because we have a lot of parameters that we have the network needs to basically learn to be able to segment the images. So we're going to see our code now first. We are importing our UNet 2D that we just coded, another important keras functions. We're going to set some parameters. First, these parameters are basically flags that we do want to train the model, that we do want to save the weights, that we're going to preload some weights that we had from previous training. That's because if we only train for one epoch, that's what we're going to try now, the model is probably not accurate enough to segment an image. But in the case that we already have a model with 40 epochs, then we are only going to get like a 41 epoch model, and that's really accurate, and we can segment with that. We don't want to test right now. We're going to test the model manually later. There are some data paths that we need. For instance, the path to the train data, the path to the test data, so the folder where they are stored basically, and the folder where the preloaded weights are stored in these 40 epochs here. Finally, the most important parameters are these: the input, the output, then the number of epochs that we want to train, the numbers of steps per epoch. This is, in every step, all the images are going to be taken in batches of 8. Finally, data augmentation parameters. We don't want to train the network only with data that we have, but also with augmented data. And how do we augment this data? Well, we have prostate images, but then we are going to rotate them, shift them, move them, zoom them, etc. These transformations that we do to our data are going to make the network more robust, because if we have a prostate that is perfectly aligned with the training data, then it's going to segment correctly. But we also want it to segment correctly when it's not perfectly aligned with the data that we have. So if it's a case where the prostate is different, then we are also covering that through this augmentation. And then the code for the training itself, we first augment our data here, then we define our UNet model, then we preload the weights that we had from the previous network, And finally, well, we are saving for a future. We are also saving the weights, and then finally we train the model with this fit generator. This is a Keras function that is included in our model because we use a Keras backend in our UNet, and we use the augmented data for this. Finally, we are not using this. That's why this flag is false. And finally, there is some post-processing and save the results that we are not going to discuss in this tutorial. And finally, we just run the code and start to augment the data, save the weights, and start training the model. We can see that it starts with epoch 1 of 1. And this is going to be a long process, so we are not going to show it completely, but we are going to show at least how it starts. So it started, it took around 1 minute to train the first epoch, or a little bit more. We can see that it already has high accuracy. That's because we already had preloaded some of the weights, and that's why it's a little better than it would be from the beginning. From the beginning, the first accuracy should be around 60% or 50% or less, probably even 30. And now it started already with 97%. That's a lot. So we can see that the preloading step, if you already trained the network before and you want to make it better, it's a really important step because it saves you a lot of time. We are not going to show the entire process because, as we say, this is a really long process. But when it finished training, we are going to show you the testing step. Now the training is finally finished. It was a long process, but it can be faster with the proper computing power. The accuracy of the segmentation is now 97.5%, and the loss has dropped all the way down to 4.5%. It's not a big increment, but that's because we already had a pre-trained network with 40 epochs. Ideally you want to have many epochs because you have to expose the network to all the images several times, so it gets exposed to all the augmented database that is probably really huge. These are good results, of course, but these are training database results. So if we use new images now, perhaps the results drop down a little bit because of overfitting. We are now going to proceed to test the network in a set of images that was not in the training set. To do that, we are just using a piece of code that we already had, a snippet of code that we prepare for the testing step. From this code, we want to see two things. First, that the segmentation is done correctly. We are going to use an image and we are going to try to see if the segmentation is done correctly. And second, we will see that the segmentation process, once the model is already trained, is really fast. Now we run the code, well, we are using only one patient. It's 55 slices. This is a UNet 2D, so it will make one slice per segmentation. But you can see that for every slice, it only takes about 1 second to segment it. So it's really fast to segment. We can already say that. It will take around 1 minute to segment the entire patient. And then we will try to check the results and see if the accuracy is more or less correct, or at least if it's similar, the segmentation with the UNet is similar to a segmentation that we already have performed manually. That is going to be our gold standard. We are now going to look at the results of the segmentations that we just performed with our network. These are prostate images, as we already said. And first of all, we need to clarify that after performing the segmentations with the network, there's some post-processing that one needs to do. Mainly, the segmentations that we get are basically a percentage of probability of how likely a pixel is to be part of the ROI of the segmentation. Basically, if it's more than 50%, we're going to say it is part of the segmentation, and if it's less, we're going to say it is not. That's the most normal approach, but you can select whichever percentage that you find appropriate. Then you can also do some other things. For instance, sometimes there are holes in the segmentation, so you can try to post-process to avoid holes if you think that that's part of the segmentation that you need to do. In any case, we are not going to cover that in this small tutorial. So this is the image, the original image, and we are basically going to open and import the segmentations that we just performed. This segmentation here, we can see that it's rather accurate. We can see that it follows the prostate rather correctly. And when there is no prostate, that's also interesting. In the slices that there is no prostate, it accurately interprets that there is no prostate. So sometimes the segmentation could just go on forever, but in this case, the segmentation even understood how to segment when there is no prostate. The segmentation is quite good, so we can say that this was a success. I remember that we basically already had a trained network, and we only added one extra epoch, so in total we have 41 epochs, and that's why this is a good segmentation. Normally, with the first epoch, you wouldn't get such good results. And on that note, we finalize our tutorial. I hope you enjoyed it. Thank you for your attention. If you have any questions, you can send me an email. And I hope that this will be enlightening for all of you, and I hope that it wasn't too long. Bye.